Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to help the viewer understand what is gravitational potential energy and also why we can use it in the work energy theorem the way it's used. So what I want you to consider here is this young lad Timmy here. And we're going to talk about the gravitational force acting on Timmy, and the first thing I'm going to do is I'm going to go ahead and put a force vector on Timmy for the gravitational force of attraction between him and the Earth. So we would represent that with a vector that points down. All right, and that's what we call his weight, or I like to also label it as mg, because ultimately that's how it's calculated. Now, I'm going to consider a couple cases here. Timmy, imagine now, wants to get to this position right here. So I'm going to call this position 1 and this position 2. And we're going to look at, in this video, several different paths that Timmy could take. Now, I'd like to point out right now, this is not a complete free body of Timmy. The complete free body would have normal forces at his feet acting up. But the purpose of this is not to draw a complete free body. Again, I just want to focus on this force right here, the gravitational force. And I want to kind of investigate with you the work done by that gravitational force as Timmy goes from position 1 to position 2 along several different paths. So let me talk about path 1. Maybe somebody somehow puts a ladder here or something, and then Timmy climbs down the ladder to this position and then walks over to here. So the ladder has a certain height here, or a certain length. I'm just going to call this h, and I guess h really isn't the length of the ladder. It's the height that Timmy is off the ground measured to what's called the center of gravity. That's not really important for this video. Basically, the height is from the ground to Timmy, we'll just say. And as Timmy climbs down the ladder to this position, right, and then moves over to here, I'm going to call this path 1. Okay, and let me get rid of the arrows because it's going to get kind of messy. But again, path 1 is going to be down and then over. The work done by gravity as Timmy moves down is going to be easily calculated. The force is mg, and then the distance is h, and that work term is positive as Timmy moves from this position to this position, and that's because the gravitational force would be in the direction of motion. Now, as Timmy walks from this position to this position, the work done by gravity is 0 because the gravitational force is still down, but Timmy would be moving from left to right. So remember, only forces in the direction of motion do work. The total work done would then be equal to this term, mgh. That's the work for Timmy to go from here to here, and then from here to here. Right, now I'm going to look at another path that I'm going to call path 2. And in path 2, what we're going to imagine is that somehow, maybe somebody, I don't know, takes a board or a beam or something, and it's nailed down so that Timmy can walk along this path. And then he gets on a ladder and drops down to here. Now again, not extremely important about the ladder and the details there. Just imagine that in some way, shape, or form, Timmy moves this way and then down. So for path 2, the first part is Timmy moving along this horizontal path, and the work done during that part would be 0 because the gravitational force is down. However, Timmy would be somehow moving to the right, and again, there's a right angle between the gravitational force and the displacement. Then Timmy somehow climbs down a ladder or rope or something, and the work done from that second part is equal to mgh. So the total work done for path 2 is going to be 0 plus mgh. Again, 0 because there'd be 0 work done by this force if Timmy were moving horizontally. And then the work done would be mg times the height h as Timmy moves from this position to this position. The total work, you'll notice, is equal to mgh. And again, positive. All right. Now I'm going to draw another path. Imagine that Timmy moved along this path. I'll go ahead and draw that one and keep it in here. Somehow Timmy, I don't know, maybe this is a giant board or something that Timmy walks down. So here, what I'm going to do is draw another picture of Timmy. I'm going to put Timmy on the board. And I'm going to put that force vector here because this one requires just a tiny little bit of math. So that force vector, whoops, would be straight down, equal to mg. And when we're calculating the work done now for path 3, and again, path 3 is going to be along this path right here. All right, work is force times distance, but only forces in the direction of motion do work. This force, you'll notice, is not directly in the direction of motion. So what I'm going to do is I'm going to use a little bit of right angle trigonometry. Now, if you're familiar with trig, this will not be a huge deal. If you're not, just watch the video, and the main points of the video are not 100% dictated in understanding this part. So just let me get this done here. But this force vector here can be broken in what are called vector components. It has a component this way and a component this way. And basically what that means is this force vector can be thought of as the vector sum of these two. And you'll notice there's some sort of angle theta here between these. Now, it's not very tough mathematically to show that this angle theta is the same as this angle. When we calculate the work done by the gravitational force, remember that only forces in the direction of motion do work. So if I'm going to calculate the work done by the gravitational force as Timmy moves along this path, one way to do that is by taking this force, because that is the force component that's in the direction of motion, and that force component is equal to mg times the sine of the angle theta here. Now the reason this right triangle has a hypotenuse equal to mg, this side is opposite the mg, and the sine function, remember, is opposite over hypotenuse. Again, if you haven't had any trigonometry, this part's not extremely important for the video. I'll just ask that you'll take my word for this part of it. So we have the force mg sine theta. That's this. That's the component of that gravitational force that's in the direction of the displacement. All right, then we would multiply by whatever this distance is right here. So for now, I'm just going to call that d, capital D. Now, you'll notice that so far this looks, quite a bit different than the first two. However, if we kind of inspect the trigonometry of this geometric triangle right here, keeping in mind that here's an angle theta and I've called the hypotenuse d, sine of theta is equal to h over d. So this guy right here can be written h over d. And when we place this here, you'll notice that when I write this out, mgh over d times d, these now cancel and we get mgh. All right, so let me get to the point of this video. I've just demonstrated over 3 different paths. Path 1, path 2, path 3. In all 3 cases, the work done by gravity is equal to this term, mgh, 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 right? In fact, it turns out that the path doesn't matter at all. Timmy could take all sorts of bizarre paths, maybe some sort of slide, maybe some sort of kind of inverse concavity slide or something like this. Or he could actually fly in the air and do loop-de-loops. As long as he starts here and he ends here, the work done by gravity is going to be the same, mgh. Furthermore, you'll notice that the left-right, like this distance, never came into play at all. Right? It turns out that, let me get rid of some of the stuff here. It turns out that the only thing that matters when calculating the work is the height difference. See how in every term, h, h, and h. So what I'm going to do is I'm going to put a couple of green horizontal lines here. It turns out that, oops, I'm going to draw this one in green, another one down here in blue. It turns out that no matter where Timmy starts, left or right, and no matter where he finishes, left or right on the blue line, the work done by the gravitational force is equal to this quantity, mgh. That's why we can define that as a potential energy. So in this example, if I wrote out the work energy theorem, PE1, let me do so in black. Right, PE1 plus KE1 plus work equals PE2 plus KE2. As long as position 1 is anywhere along this green line and position 2 is anywhere along this blue line, then the work done by gravity as Timmy moves from 1 to 2 is equal to mgh. And that's what allows us to say, all right, well, I'm going to maybe call this a datum here and say that PE1 is mgh. And then we would say that PE2 is 0, which is perfectly fine. And then you can proceed with the rest of the problem. Another way we can work it is we can call this green line here the datum and say that the PE1 term is now 0, the PE2 term is minus mgh, minus because we're down below the datum. The third way we could actually work this problem is we could ignore the term potential energy and pretend like we've never even heard it. And basically just say, I've never heard of these. But as long as Timmy starts at green, ends at blue, the work done by gravity is positive mgh. So you'll notice in all three cases you end up with something that's basically mathematically equivalent. Whether we put a positive mgh here, a negative mgh, the potential energy is the work done by the gravitational force as Timmy moves anywhere from this green line to anywhere on the blue line. And because that work doesn't matter where he is, left or right, and it's the same value no matter what the path, even if he does some sort of crazy path, because we know that value, we can just give it a name. We'll call it a potential energy, and we can put it under either of these two terms. So again, the purpose of this video is just to help the viewer understand why we can define a potential energy term for gravity, and that's because the work done for gravity is the same as this young lad, starts at green, ends at blue. And a big part of why we can do that is because the work done by gravity is not path dependent, right? So, gravity is an example of what's called a conservative force. This video is meant to be very conceptual. If you've had a little bit more math, you want to see a little bit more about conservative forces, look up one of my other videos about conservative forces or other conservative types of vector fields. But for this video, it's just meant to be very conceptual. Because the work done does not depend on the path, we can define a potential energy for it. As long as he starts at green, ends at blue, we know that the work done is going to equal this term, mgh, and that's why we can call this a potential energy term. So anyway, I hope this video helps with these concepts. Have a great day.